What I'm going to talk today is about how to do natural language processing on social media data. Now, social media is an amazing resource and it has lots of unstructured text, and we can do lots of things over it, and people have been doing a lot of things over it. Now, the question is, the standard natural language processing tools that we have, do they work on social media? And if they don't, then what we should do. So I'm going to talk more about what are the problems, challenges, and how we can tackle it. I will also try to point you to some of the existing tools, because many of you will need those tools for your projects, but there are caveats, and I will mention it when we come to that. So I will start with talking about what are the main features, why NLP for social media is such an important field today, and what are some of the challenges and opportunities in the field. Then we'll move to techniques and wrap up with some case studies. Don't go by the time things. We won't spend so much time on case studies. Probably we'll spend more time on techniques. So why NLP for social media? Now, this is a buzzword of the previous era, big data. Today it's deep learning. So social media is an ideal example of big data. And the reason is, apparently big data is characterized by three qualities: volume, velocity, and variety. And social media has all of them. Just to give some examples, these are a little dated statistics, probably a year or 2 years old. But nevertheless, they are huge. So the numbers would have only grown by now. So 1.3 billion monthly active FB users. So this is a huge number. So you can imagine the amount of text, in terms of volume that's there, generated every second, in fact, on Facebook. Velocity, how fast the text keeps coming, or the data keeps coming. So 5,700 tweets per second, or 2,500 messages on Facebook per second. It's a huge amount, huge velocity. And of course, variety. So there are multiple scripts. I'm just talking from language perspective, the variety. So you have lots of different scripts, styles, topics, everything being covered. It's hard probably to think of anything under the sun which is not in social media. So you find all kinds of things. In fact, one interesting anecdote is somebody has launched a project about saving endangered languages by mining Twitter. Or rather than saving, documenting endangered languages. So there are some 6,000 languages in the world, and one dies every 2 weeks at present. So more and more people speak English, and languages are dying. Well, not English necessarily, but only some of the languages. Now, there is very little data to document about those endangered languages, and interestingly, you find tweets on them. Maybe not much, but people have tried getting those. So it's a huge variety of data. And of course, as I said in my previous talk also, that probably more happens on social media, on the virtual world, than the real world today. So you have data about everything: where you went today, what you wore today, what you ate yesterday night, everything I know just by looking at your Facebook feed. And of course, it's impossible to process and consume this data using any kind of human intervention. So everything has to be automatic if you want to do anything with this kind of data. And what are the kinds of things you want to do? Some are like real needs that come just because you want to present people this data or this information. So one is you want to navigate through this data. So how do you provide tweet feeds? For this, you need to do some kind of processing over tweets. Now, most of this could be pretty dumb, like you just use hashtags, but nevertheless, you have to do something. And then if you want to see on a topic what's happening, so you want to summarize, so then you have to do NLP. Now, if you see most of this, all these TVs, NDTVs and all, every time I see, they are talking of, okay, this celebrity tweeted this, and there was this backlash, and there were this series of tweets. So most of the journalism today, or a major part of journalism, is based on social media. So for them also, it's very hard to handpick tweets, and it would be very nice if somebody could look at all the tweets and characterize it. So it's like, what is the trending topic? What is the sentiment about this? So all these polls and other things that used to happen through surveys, Today you don't need to do surveys. You just go and see how many people are pro-Trump, how many people are pro-Hillary, posting things on the Facebook, and you have or Twitter, you have a good estimate of what's happening. And then there's another reason why people want to do things, which is, you want to filter certain kinds of posts or data. One is, of course, inappropriate content like adult content filtering. So if you are below 18 years, your parents, you could still be on Facebook probably, but your parents might want certain filters to be set for you. And in that case, we need filter on the content and stuff like that. Rumor is another problem. Now, there has been lots and lots of studies, and I don't have any of these case studies today, but it's one of my personally favorite topic, like how rumors spread over social network. And you'd see a lot of them starting from really valid, seemingly valid scientific truths, like, cancer is not a disease, it's deficiency of vitamin D17, to all the way down to politics. Politics is all about rumors anyway. So you find all these kinds of things and how they spread. So people have been interested about solving these tasks for a very long time. But another thing which is also very, which is kind of a side effect of all this data is we can now understand and study human behavior in a much better way and a data-driven way, because we have a lot of data to do this today. So as a result, it has been one of the hottest emerging, I should not say emerging anymore actually, probably the slides are a little old, 2 years old. So it's already a very hot area in NLP, and it has been so for at least last 6-7 years. There has been special sessions in big conferences only on NLP for social media. There are tracks on NLP for social media in ACL and NLP. So this is one of the very hot areas. Now, are there any challenges? Of course, we did say there are interesting things that we can do. We'll see more. Are there any challenges? So here's a photo that I had posted on Facebook. So this is what I do when I go to conferences. So this is a Thai cooking class, and it's in Chiang Mai. So I'm learning how to cook Thai food. And I posted it on Facebook, and you see a lot of comments. I don't know if you can read them, but if you read those comments, you would find very interesting things. So let's say this one, right? Anybody recognize the language? It's Bengali. And what's happening here? It's English, but something interesting happening, right? What is this word? Abe. A-B-A-E. Abe. Abe, what's going on? So you see that. If you see this comment, what language is this? Contest na class. This is mine. It's code mixed, and actually it's Bengali, but most of the words are English. So I'm saying it's not a contest, it's actually a class. So all sorts of things are happening. Typically you see that, like Abe, what's going on is typically how we say things, but not write things. But on social media you would see this kind of conversation, or this kind of text which is more towards speech. Then there are non-standard spellings. I don't think here there are too many examples, but of course you know that there are. And you have tags, emoticons, and all sorts of things. Of course there is mixing of language like I showed here. Even this one, Kothakar Master Chef contest. So this word is Bengali and the rest is English. So you see lots of this mixing of languages happening. There's transliteration. So there's Hindi and English here, but you won't see Devanagari script or the Bengali script, right? It's all Romanized here. So all these things are happening, and you have to tackle all these things if you have to understand this data or do any kind of processing over this data. Now, what kind of things are happening? So you have to, traditionally when people built NLP systems, they always assumed that the data that's coming, and I'm talking of text systems. Speech systems have always been different because speech doesn't follow any grammar. So speech grammar in the sense, it's not like the text grammar. So it's pretty, there is a lot of individual variation and a lot of different things that happen. On the other hand, for text, people have always assumed, okay, I have a grammatically correct text, mostly there are no spelling errors, it's written in a single language, in the right script. So all these were assumptions that people made when people built the original systems. And then they started failing one by one. So around 2000, all these new fields started, which the top broadly it's called computer mediated communication, where two people are communicating, but there's a computer sitting in between. So it could be email, it could be chat, it could be even like not necessarily a computer in that sense, any computing device like a mobile phone. So it could be your SMS. So all these are part of computer mediated communication, and things started, failing in the sense. Suddenly people realized that on SMSs, none of these techniques work. They are too small, there are too many contractions, so we have to do something different for SMSs. So around 2005, there was a noise about working on SMSs. We called it at that time texting language. And I myself worked in 2007, I will talk about that work a little bit, on how to normalize SMSs. Then around 2010, with Twitter, people had, a lot of enthusiasm that, okay, now we have this humongous data source coming in, and we know NLP, we can do lots of things, and they found that most of the techniques would fail. And lots of problems which are thought to be solved suddenly became very important. For instance, one problem which I think exactly in 2010 or 2005, I forgot the year, was declared to be solved, which is language detection. So you need language detection to do information retrieval. So you need the language of the web page to do detection, right? So it's a very old problem, and people have tried to solve it. And if you imagine, given a document, identify the language, and usually documents are no spelling error, single language, the right script, it's extremely simple. Most of the time, the script will tell you which language it is. Sometimes like the Latin script, which many languages use, or Devanagari, which many languages use, you need to look at the word distribution or character distribution. Just sheer short answer that you get with only like a paragraph of text. But so somebody wrote in 2005 a paper, language detection, a solved problem, good for first year assignments. It was really a paper. And then just after a few years in 2005, 2010, somebody wrote a paper, language detection far from a solved problem. And it was primarily because of Twitter, because of all the contractions and all. Even today, forget about code mixing. Imagine that tweets are coming in single language. Twitter detects, the Twitter API, the Google API, the Microsoft API, we have tried all of them. They detect around 100 to 200 languages, depending on which API we are talking about. But the error rate is as high as 20%. So they do very well with English, Spanish, Japanese, all these languages. But when it comes to, let's say, Hindi transliterated, they will immediately say Indonesian or Estonian. And if it is not even transliterated, let's say Nepali written in Devanagari, it will immediately say Hindi, because anything Devanagari it thinks it's Hindi. So none of these are like small languages we are talking about, right? Spoken by billions, millions of people. So with all these things, the landscape has been changing, and I talked about it also previously a little bit. So what's happening here is initially we assume things will be, text will be always text-like, which is very formal and with a proper grammar. So that's like one end of the continuum. On the other hand, the other extreme, like if you imagine casual speech, we do all these things that we already said, right? We stop in the middle, we do not finish sentences or phrases, and do all sorts of things. So that's, they're the form, especially if it's a casual speech, not a talk or a formal recitation or something like that. So that's the other extreme. And if you try to plot all these things where they lie, you will see that they, kind of fill up the continuum, and different things fall at different places. So usually tweets are a little more formal, because it's usually a broadcast. You are trying to reach a larger audience. But if you look at chats and SMSs, so I will tell you our experience when we were trying to normalize SMS. The first thing you need to do is collect data, right? So you, at least for testing. So we collected some 100 or not 100,000 SMSs from a website. It was called Treasure My Text. It was very funny. We thought, where would we get SMSs, because there is privacy concerns and other things. It turns out in those days in mobile phones, we didn't have enough memory, but you might still want to treasure your text. So there was this website where you could upload your text. So a lot of people had uploaded, and anybody could go and see those, actually. So we downloaded some 1,000 SMSs from there, and we tried to normalize them manually so that we have a test set. And when we were trying to normalize, I mean, most of the people were familiar with SMSs. It wasn't that they did not know how to type SMS, but it was extremely hard. I mean, for one particular SMS, 3-4 people would sit together and try to decipher what it is and what should be the right thing. And that's because it's a personal communication, and often you use abbreviations which only you know and your friend knows. So it's on the left side of the continuum. Kalika will probably tell you about when she was translating Twitter for an experiment, tweets to Hindi or to English, Hindi tweets to English, how hard it is. I mean, it's very hard to make sense of those things. So we are talking of how to process things which lies in this part of the continuum, right? Rather than this, which it's not solved, but we can do much better. But there are opportunities. We have lots of data. And one thing is speech data is very expensive, like Alan was telling yesterday, how it's difficult to get good conversation data. Now, these are not perfect maybe, but at least some source from where you can start your processing. You get a lot of personal conversation, and also thankfully people don't care if you look at their personal chats. So on Twitter and other places, you'll get a lot of personal conversations through which you can model things. The other interesting thing is this data is socially grounded. So you don't only know what is being said, but you know who said it, from where. So tweets might be geolocated, then at what time of the day. Then about the user, you might know what gender the user has, what educational background, what languages the user know. And between users, you might know whether they are friends on Facebook or not. So there is a lot of social information, demographic information that comes along with. So which can, help you do more sophisticated analysis. So you can correlate language use with things like demography, social relations, personal relations, and so on. And therefore, and the other thing is language on social media. I mean, in general, language is a dynamic entity, right? Language changes over time. And this was my PhD topic. So how language, let's say, Sanskrit eventually became Hindi or Bangla or Odia. So how to model that process computationally. The main problem you have there is language changes over a very long time. So typically, let's say, 100 years, 300 years, 1,000 years. So that's the time scale you look at to get a reasonable amount of change. Now, if I want to model these and want data to validate, how am I supposed to get data of, how Hindi was spoken? Let's say Hindi didn't exist then. Let's say whatever the precursor of Hindi was spoken 300 years ago or 500 years ago. Where do I get data? There is very little documented data, mostly text, no speech at all, and you have to kind of extrapolate from that and make your models, right? Now, what happens with social media is you can actually see the change happening very fast. And that's the reason why the last problem in my PhD I chose was SMS language. My idea was to show how people creatively change the language in texting. What are the forces through which they change it? I mean, forces in the sense pressure of one of the objective they are trying to optimize is how to type with as few characters or as few keystrokes as possible, right? So how those objective functions actually people creatively try to optimize, and the language changes over time. It was hard to see because we didn't have Twitter at that time, how to see how your language would influence my language, which is a very important part of language evolution. Because if only I use a convention, that's not a convention. All of us have to use a convention, and then it becomes part of the language. But with social media, you can see one hashtag comes, it becomes trending over time, and millions of people use it, and soon it becomes a word. So this is a way, it happens in matter of weeks or maybe sometimes days. So people have been studying all those things, also using social media. So if you have any questions so far, broadly about the topic, you could ask. Otherwise, we will move to how to process the data, or even why do we need, is there a need to do it? in the sense that would current techniques work? So let's start from this point that we have NLP techniques to solve a lot of different problems. If we apply it on social media data, is there a problem? And many people have done these experiments. I took 3 examples. One is machine translation, another is part of speech tagging, and the last one is sentiment detection. Now for machine translation, one of the very good open systems out there. So WMT is a workshop on machine translation, and Moses is an open source system that you can train for if you had parallel data for any language for machine translation. So for some English-Spanish data set, which is like not social media text, more like proper, regular, formal text, the blue score is 35. Now blue, if you don't know blue, it's okay. You just need to know that higher the better. So the exact same system, when these guys, Hassan and Menzies, they are my colleagues in Microsoft Redmond. Arul leads the machine translation team, Arul Menzies. So when they applied it, the blue score on that particular data set was 29. So it's the same language pair, more or less the same topic and everything. The only thing was this was properly written text and this was some social media text, and there is a drop of 6 blue points. In this particular example, right, part of speech tagging was one of the first problems that people tackled with machine learning back in 1990s. And it's kind of a solved problem. So you get 98% accuracy. There is this Stanford tagger and many taggers for English that on standard text will give you 98%. Now 98% is supposed to be very good or impossible to beat, because if you ask 2 humans to tag, annotate data, 2 linguists to annotate data, they don't agree more than 98% of the times. So it's probably as good as it can get. But the same tagger, when Gimple they applied on social, again, I think it was tweets. On tweets, the accuracy was 85%, English tweets. So there's a huge drop, right? And similarly for sentiment detection, it was 92% on some standard data set, and on tweets it was between 70 and 80%. So there is a huge drop, undoubtedly. And all these people were probably doing some pre-processing, but let's say removing hashtags and URLs and those kind of things, but not a whole lot. Nothing specific to social media. So there was a good drop. Now the question is, how can we improve it? Now there are 2 approaches. You could think of, one is normalization. You could normalize. So let's say this is a tweet, and the normalization system will take this string as input and give this string as output, which is more like a formal text. And then now you give it to the standard system, and the standard system can work on it. So let's say we were trying to solve the machine translation problem. You have this English tweet, it got normalized into this, and then now the standard English to Hindi machine translation system would probably work, and it will say something like this, which is right. So essentially here you have to build this piece, and this you rely on all the standard things that exist. So this is a good approach because this is very scalable. If you build any normalization system which is good, you are done. You can solve all other NLP tasks just because the systems exist. The other thing is, of course, you could build a system from scratch. You could say, oh, let me just collect a lot of data in a lot of English tweets, translate them to Hindi tweets, and take a lot of Hindi tweets, translate them to English tweets. That gives me a parallel data. I train a new English-Hindi tweet machine translation system where this is the input and this is the output. Okay. Now, do you think any one of them is better or more preferable than the other? Or let's take them one by one. What's the problem of this? Data is one big problem. You have to collect a lot of data. And for every task, you have to collect different data. So this is for translation. For pause tagger, you have to collect lots of tweets and then annotate them manually to create the training data. For sentiment, you would again have to do the same. So that's one problem, data. Any other problem? For each language, you have to collect. Yeah. So true for even the normalizer you have to build for each language. So for Hindi, it would be Hindi, right? So if it was a Hindi tweet, the normalized output would be standard Hindi. Yeah. So one major problem here is you are not leveraging any of the work that has already gone for last 50 years in building these other standard NLP systems. So that's another problem. So normalization seems to be a good thing to do. But can you think of any problem with normalization? It's hard, yes. So therefore, not necessary. So this is the problem we faced when we were doing the texting thing, right? So we were not sure what the person meant. So TB might mean tuberculosis, might mean text back, might mean many other things. And we didn't know at that time, in the context sometimes yes, but not always. So that's one thing. So that's why it's a hard problem. Yes. Yeah, so this is the biggest problem actually. So errors propagate and accumulate. So it won't be perfect because it's a hard system. And when the errors come in, so this will probably not look exactly like this, but let's say these THESC is a tweet or something like that. And that error will ve ek tweet hai kind of thing, it will come up, right? So it will, I mean, if I'm assuming the empty system is not doing an error, empty system will also do an error, and finally the output would look like यह एक पक्षी है, something like that, right? So it will be completely random. Now, so that's a big problem of normalization, and people don't want to do it. The other problem of normalization is, sometimes things are just not normalizable, like Saptarshi was saying. It's just that this is a different language altogether, and you don't have an equivalent in the thing. But you could actually, in the same model of language, you could do things with it. So for instance, I will show you in pause tagging, you might have altogether different sets of part of speech, which doesn't apply to normal English, but works perfectly in the case of tweets. So you could treat it as a new language, and that gives you other benefits as well. So we will go through both, I will show you examples of both. So in the case of machine translation, Hassan and Menzies, they did a normalization. Just by normalizing the tweet, it went to 32. So from 29, it went to 32. Still, it did not reach 35 because of normalization problems and maybe other problems, but you can improve. On the other hand, in this work, right, they built a pause tagger from scratch from Twitter, and from 85, they went to 89, but still there is a big gap between 98 and 89. So a lot of scope for improvement, but here we don't know. I mean, we have to do such experiments again because tweets are not normalized but directly annotated, right? So how well humans annotate? So the baseline here is 98%. Humans can do it with that much accuracy. The baseline here may not be 98%. Probably it was 95 or something, but still there's a good scope of improvement. So similarly here also they showed that tweet specific things, if you do, it will improve sentiment analysis by a little bit. There is another problem, another set of problem. This is just one problem, which is the informal language. But the other dimension of variation is that, when it comes to text, typically formal text, it's written by a class of people who are typically educated in a formal sense. They have a basic level of education. So if you read newspaper articles, they are all written by reporters. Reporters have a basic level of education. There is an editor sitting on top who corrects it in a certain way. So therefore, the language of those are very specific. And there are very interesting things people have observed. So when you take this kind of, let's say, newspaper articles, or one of the most famous English corpus is the Wall Street Journal corpus. So a lot of things are trained over it. And it turns out that typically those articles are written by older people or even, I think, older men. So that's why any parser trained on Wall Street Journal works very well for language written by older men, but not so well by younger people or, let's say, women. So there was a very interesting study on this. So language varies from person to person. Of course, geographies to geographies, but every individual, it varies by gender, it varies by age, it varies a lot, right? So here was a recent study in last EMNLP. They showed that if you took, so Twitter has lots of, so good thing about Twitter or social media in general is it's much more democratic. So you have everybody typing in, right? So they had a way to collect African American tweets, and they had, I mean, I'm not getting into how they actually did it. It itself was a hard task. And of course, white English, so white American English. And what they did, they took a couple of existing parsers and tried to parse these tweets. It turns out with African American English, the accuracy here was 64%, whereas this for white English, it's 80%. It's very big difference, right? So, and as a result, I will tell you what happens as a result. This is 50%, this is 71%. As a result, when you do any aggregate, right, you tend to throw away a lot of things where your confidence of the system is low, and essentially you typically throw away these things. And your aggregate view will mostly show the view of probably these people. So in India, it happens a lot. So when people do social media analysis of India, they throw away all Hindi tweets, all code mix tweets. They keep only the pure English tweets. But they actually show a very different viewpoint than the entire population's viewpoint. So it can go with the language also, but this is interesting because in the same language, there's a big difference based on what dialect they are or variety they are speaking. So similarly, we actually showed another dimension of variation is language mixing. So in standard, a standard Hindi post tagger or an English post tagger has, let's say, 85 to 95% accuracy on tweets, whereas the same post tagger, when applied to code mix text, it gets to 55%. Not a very, surprising thing, because if you think of it, 50%, it's code switched and there are two languages, and it's only getting half of the things correct at a time, each post tagger. So there are other dimensions of variation that also makes things more complex. So I'm going to talk about both the techniques by taking, both normalization and how to build things from scratch. The aim here, the reason I picked these are because they illustrate some very different types of approaches. And my aim here is not, tell you a little more about along with the technique, the research methodology, how you approach the problem, especially in the case of when you build something from scratch, because that's very important, how you test it, how you, design the data sets, etc. So that's what I want to give you a glimpse of. So let me start with the normalization techniques. Yep.
What is the overall goal of, let's say, English quick output you want to translate to Hindi? Twitter being informal, so long as it captures the intent and the sentiment, that's more important than capturing the language structure. So is the question of parts of speech recognition as important? If you're just going to say, if I can convey this intent to this person in this language, that is good enough, because the output need not be in a full formal sentence.
So there are two things here. The first is I just took this as examples. You could think of even the problem that you said will have the same issue. So even like the sentiment, I just showed an example, right, will have the same. I took this. The second is, if you see, right, translation, Facebook, Twitter, everybody would have a translate button now. Twitter uses the Microsoft Translator. Most of them don't do anything. I don't know what Facebook does, but I know Bing doesn't do things very specific to Twitter. So it uses the standard translation thing. So when tweets get translated, the sense is not conveyed at all. You would see it's all garbage. Facebook comments, all mostly garbage. It's much better if you translate a Wikipedia article, for instance, or a news article.
Yeah. It's as important, it's not for the formal structure, but even to understand the intent, you need the part.
Yeah, so post tags goes as features in a lot of these things. Yeah, but in one sense, a lot of these things are disappearing with deep learning. So people are not doing step-by-step analysis. But the problem with deep learning is then you need a lot more data to train it. So I don't see how deep learning is going to, I mean, for English probably, but how it's going to change, how we do Tulu language processing. So if you want to do something for other smaller languages, Hindi also probably, if governments pumps in more money or companies pump in more money, we will probably replace everything with a single deep learning box, magic box. But it's not going to happen with all languages. So these systems try to build on top of structures at lower level. So I'm going to talk about these three techniques in the normalization. The first one, it's one of the very traditional approaches. This was the work that I was talking about when I did back in 2007, part of my PhD. So here the approach to normalization is sort of what you call the translation metaphor. So you have the standard language text coming in as input. It's going through a noisy channel. This is the famous IBM noisy channel model of translation. And out goes your texting language or social media language. And you have to learn the characteristics of this noisy channel from the data. So that is the main goal here. A lot of systems are built in this way actually. Even speech decoding is kind of built in this way. And essentially what you try to do is, it's a very simple, you apply Bayes' rule. So what you have is, you actually are seeing this, right? Not this. So you assume that the standard language goes in, noise is added, and you get the texting language as output. But you are seeing the texting language, and your aim is to recover the standard language. That would be the normalization process. Now, how do you do that? So you assume I want to predict this ideal standard language string, which actually the standard language string that maximizes this parameter. What is this parameter? That given this texting language string, what's the probability of seeing, so given a particular t, what's the probability of seeing a particular s, and over all such s's, I am choosing the s which has the highest probability. And then I apply just Bayes' rule and break it up into two quantities. So one is, so it's a simple application, and you have two parts. The first part says, given a particular s, how would t look like? What's the probability of seeing the t? So that is essentially the channel model. And this is like what in general s would look like. So given any given s, standard language, is it valid string of English? So that's the language model. So this is the channel model, and this is called the language model. So essentially to learn this, solve this problem, you have to learn the channel model and the language model, and then combine the two to decode. Everybody gets that? Okay. So how I build the channel model, I am not going to tell you here. So what we did broadly is we made HMMs for the channel model. So you have, so you can imagine what kind of creativity you could do, right? How can you be creative? So you could just drop things. So delete characters. It's very common, right? So if you write introduction could just become intro, or a big word like let's say chair could be CHR. So you delete vowels, you delete. So we had a model of deletion, and you could actually type things as you pronounce them. So let's say forest could be 4EST. So it's like how you pronounce the things, or just 4ST. And then seeing is C, the character CIN, something like that, right? So you could, so we had a model for these different kinds of operations, and the mathematical tool that we used was a hidden Markov model. So those details, if you are interested, we can talk later, or you can look at the paper. But for each word, it gives something like this. So at the end of the thing, if you have this as an input, it will say, okay, this can be output with some probability. These are, negative log probabilities. So higher means it's more probable, and lower means it's more probable. And so you have today, to day could be today or stay or away or play or clay, whatever the system gave. And you see the good thing is here, the difference between these two numbers, and it's in log scale. So actually a difference of, let's say here 8 means 8 orders of magnitude different. So today is far more probable than any of these words. But it's not true for everything. So if you give FNE as input, it says it could be fine, it could be phone, it could be funny, it could be find, it could be finds. It gives out all the words from the lexicon and their probabilities, and these probabilities are not that different. I mean, these log probabilities are not that different. So in case of today, you might just look at these values and say, okay, this is the right answer. In this case, you can't. It could be any of these things, right? If I had shown FNE. So how do you do it? So this is the channel model. Next comes in the language model. So suppose this is what was my original T. So for each word, I have these lists. And let's, for the time being, assume that I know that these are standard words, so I don't do anything for them. So for these words, I have all these lists. So I have multiple possibilities that I can generate now. So I could say, today I lost my find, today I lost my phone, stay I lost my find, stay I lost my phone. So this is the lattice, basically. You generate for each word all the possibilities, and you take the next word and generate all the possibilities, and you build. And then you apply the language model to find out what is the best possible interpretation. And in this case, hopefully this comes out to have the highest PS or the overall this value. So you predict that this is the output, and this probably would be the next best or something like that. So you get that. So to build such a model, we need data. We need two kinds of data, right? One for the language model, one for the channel model. So for channel model, we took these 1,000 SMSs, I already told you. We manually translated to standard English, which was a very hard task, actually. Average, there were 20 words per SMS, so 20 tokens per SMS. So we had 20,000 tokens, not all unique, of course. And we could align them automatically. That was not hard because it's kind of monotonic alignment. There is no word order swapping and stuff like that. And then we trained the channel model using word variation pair. Now, I had some interesting statistics I didn't put here. So the most varied word we saw, the word with the largest number of variation was tomorrow. It had some 23 variations in the data set. Today had some 11 or some variations. Of course, there were words like I, which had no variation. So it was a pretty interesting data set to look at. And then we used, for the language model, so typically, we could use standard language. Ultimately, the model that the predicted output is that of the standard language, right? We want a model for the standard language. I could take Wikipedia or any such standard language corpus and train and learn a language model and try to decode. We tried doing that. And it turns out that the output is not that great. So if you use a simple A-spell kind of thing, spell checker kind of thing, the accuracy on the test set was only 20%. So, and it's not surprising. A-spell would use edit distance, and these things are not based on edit distance. So A-spell would give pretty bad result. If you use no language model, just took the best, the most probable output of the channel model, then you get 58% accuracy. And then with a bigram, word level bigram model for standard language, we got 65% accuracy. This is the model that we built on, let's say, Wikipedia. On the other hand, when we took the texting language corpus itself, it's much less data, but build the model from that. The manually normalized 1,000 SMSs and build the language model on top of that, then the accuracy is much higher. So it just shows that people don't write Wikipedia-like things in SMSs. They write very different things, and therefore you ideally should build a language model from that genre of text. So this is very important, and this is a big gap actually. So I'm saying a lot of terms here like bigram model and all these things. I don't know if you know all these terms. So if you don't know, please ask. Otherwise, I'll just assume you know. Okay, so just as an aside, the same thing can be used for and is used a lot for transliteration. So here, the only thing it changes is here a string or a word comes in the source script. Let's say it's the I should have reversed it anyway. So let's say we have this word kahani. Just assume that the arrows are going this direction. Sorry for the mess up. So we had this Hindi word kahani, which is the source script in Devanagari, and out comes in Latin form, I mean in the Latin script, this word kahani, which somebody has transliterated in this. So our job is now looking at this, we have to get back this, right? So this is transliteration. Somebody has romanized and we have to get back. So you can use exactly the same metaphor. And here too, can you think of other words which could be this? Not only kahani, you could have कहनी, मुझे कहनी है. So it could be many different, and if I didn't have a lexicon, it could be kahani instead of kahani. I could have kahani, kahani. So all these variations are possible. And how do you know which one is right? Again, from the context. So you could apply on top of it the language model and find out which one is right. So people have used this, and this is like very, very standard model for a lot of tasks. Now these guys, Hassan and Menzies, do something different, and I thought I will briefly talk about this. This was, what if you do not have data? I mean, one of the major bottleneck of this noisy channel model is the training data, right? And we did create manually, we took 1,000 SMSs and normalized it manually. Now, if you did not want to do it, could you do it in some other way? So this was the question these guys asked, and they said, okay, can't we just look at a lot of tweets, and we will, I mean, in general, if I look at a lot of standard language, I know what are the valid standard language tokens. So for instance, I know making is a standard language token, taking is a standard language token. But making, mking, take tkin, these are not standard language token because I don't observe them in my standard language corpus. So they must be mapping to some standard language token, and I want to decipher them. But I don't have any data, I just have, let's say, a tweet corpus. So how can I do it? So they did this. They said, let's define something, so let's mark all the tokens which are standard language tokens. And a very simple definition could be they exist in an English dictionary, a standard English dictionary. So they marked all of them. Now, if a non-standard English, a non-standard token, let's say mkin, makin, is surrounded by at least one standard language token on this side and one standard language token on that side. And we'll find plenty of such examples if you have a large tweet corpus, right? So in that case, I define that vector. I mean, the vector is simply like two previous words and two next words, what those words are, as my context. So let's say C3 is when the left is I am and the right is a pasta. Let's say. So I am are the two left words and right words are a pasta. So you can say I am making a pasta, or you could say I am taking a pasta, but you cannot, I am eating a pasta, but you cannot say I am drinking a pasta, let's say. So not everything will fit in there. So only certain things might fit in. Now now these are all different contexts. So this could be I am a pasta, this is he is a car, so like that. So these are context, and in how many times this word occurred in this context, this particular token in this context and so on. So you make this graph. These numbers are how many times it occurred. So you observe 3 times this, 5 times this, and so on. And then what you do is a random walk on this graph. Or in other words, you are trying to calculate how many times you start, so they say, which is the relative frequency of the average hitting of those two nodes. So if you have a node like N and M, so let's say making and making, these two nodes, how many times you start from this node and end up in this node? And if that happens very often in the random walk, that means that these two words probably occur in very similar context, right? Because they are only connected through common contexts in this graph. So they do, they calculate these numbers, but also they have one, so this is what they call this L and M, but they also have another cost, which is the similarity, how similar they look in terms of, you know, the letters used. So edit distance kind of similarity. And finally, they combine these two costs to come up with a single cost. Now, this particular cost is what gives them what are the potential. So for instance, you can say take this word and calculate its cost with this, calculate its cost with this, and all the standard language words, and the one which is closest is most probably the probable interpretation. Now when there are multiple things which are pretty close, you can keep all of them as potential interpretations, and in the context different ones will apply. So they did not use any training data and they solved, and this is what that gave the 5-point blue score or 6-point blue score increase. That 29 to 32, that exam, no, 29 and 35, 35 was the original on standard, 29 was what they got without this, with this they got 32. So 3-point increase in blue point just by using this kind of a normalization without any data. But this also gives you a lot of, new data aligned, spelling variations and all, which is also good. We tried doing not exactly this, but we took a lot of Bollywood songs, song lyrics which was written in both Romanized script as well as in Devanagari Hindi on different websites, of course, and tried to automatically align using some similar idea. And that gave us a lot of, spelling variations for Hindi words, transliteration variations for Hindi words. And this last work is more recent. So we worked with Partha. Parth Gupta. He was doing his PhD at that time in University of Valencia, and we had a shared task in. There is a thing called FIRE, Forum for IR Evaluation, and where you float these shared tasks and data, and people try to solve those tasks. So one of the shared tasks was, doing search across scripts. So your query might be in Devanagari saying some song title, or movie title, say Chandni in Devanagari, but the original article might be Chandni written as Chandi in English, but you have to do across script the search. So that was the task. A lot of teams participated. So Parth also participated, and later we worked together to come up with a model for normalization across scripts. So what we are trying to do here is we are trying to say that SITRA, Sitare, and this Sitare in Devanagari and other spellings of Sitare, let's say SITAARA and all these variations, they all should be normalized to one single form. So across, and even like other ways of writing Sitare in Devanagari, if there were, so they should all be normalized. So across script, and not only 2 scripts, it can be any number of scripts. So as long as they are talking of about the same thing phonetically and in the context, they should all map to the same thing. So what we did in this particular case is we used very similar, deep learning, very similar to something like word embeddings. So we tried for each particular word, let's say Sitare, we made a word vector which was essentially some character n-gram based vector. So it could be, so I think we tried 2 to 5 gram vectors. And we knew from the data, from the training data, that this particular word and these are together. So we only need some examples of those. So we made a vector for this also, and we gave those 2 vectors concatenated as input. And then we tried to optimize the distance between where they are kind of embedded. So it's very typical like word2vec, but we are doing it at character level and for 2 different scripts. And it works very well. I don't have numbers, but it actually worked better than some of the existing normalization tools. Like if you use the Google Indic normalization API, it worked better than those kind of things. But it does require training data to train those word2vec models. Okay. Yes. Right.
So if you have that kind of pronunciation issue, can't you just make the pronunciation standard?
So you solve a different problem in that case, which is for every given token you have to identify its pronunciation, right? And these are non-standardly typed words. Yes.
Although that sort of works, what you discover is, especially with keywords with nobody knows what it is. And therefore, if you did a phonetic pronunciation, you don't know whether it should be aspirated or not. You can merge a bit, so there is some advantage.
Yeah.
But in
still a lot of noise.
And the short E, long E, those vowels are also not clearly marked, right? Yeah, so essentially it's the same problem. You are just, kind of defining it in a slightly different way. But the ambiguities remain the same. The challenges and ambiguities kind of remain the same. Okay, and this is the last bit in technique, which I'm going to show you one example of building something from scratch. And this was actually one of the very celebrated examples of doing something particularly for Twitter by, I think, Alan Ritter, Kevin Gimple, and a few more people. And what they are trying here is to do part-of-speech tagging for Twitter. And as I said here, my aim is, you may not need part-of-speech tagger, that's okay. But my aim is to show how to go about doing such a thing, right? So you have to do data creation specific to the problem that you are trying to solve. You have to find out features which are specific to social media. This might be the benefit of doing it, right? There might be, and I will show you the kind of features they use specific to social media. And you might need completely new techniques, although most of the time you would think that you don't need so. You would probably use the standard techniques, but you would use different data sets and different features. So the paper says this, I thought it is worth quoting. What are their contributions when you do such a work? So they start with developing a POS tag set for Twitter. There are lots of part-of-speech tag sets for English, but they don't apply to Twitter. This is the first thing to remember, right? It's altogether a different kind of language, so you have to probably invent there. So start from there itself. What's the useful POS tag set? Of course, they have to tag tweets, so they manually tagged some 1,800 tweets. Then they developed features for Twitter POS tagging, conducted experiments, etc. And then, of course, this is the last bit is actually very important, and not too many people do it. They released everything to the community, the code, the corpus, everything. So let's start with the POS tag set. So what's different in Twitter, right? So some things are fine, like noun, pronouns, verbs, adjectives, you will find on Twitter too. But there are certain things which they had to discover, invent new tags for. Like, so this, right, at mentions, which you would not find in normal English. Then they had hashtags. So for hashtags, where is hashtag? Yeah, so hash is the hashtag. So they had to come up with some. They had to precisely, they came up with 5 new tags. Hash and that we already talked about. This is very interesting. So they use a tilde for what they call a discourse marker, which is very special in Twitter because sometimes tweets are so short that you have to split tweets between multiple a single sentence between multiple tweets. And then people use some markers to say, in the next tweet, I'm going to tell the next thing. So it could be 1 out of 5, 2 out of 5. I have seen some people doing it. So those 1 out of 5, 2 out of 5, they would mark as tilde. There are other ways of saying this also. So whichever says that there is a continuation across multiple tweets, they use this special marker. URLs, email addresses are U and emoticons are E. So these were the new things which standard English thing doesn't use. And they of course used a much reduced tag set than standard English because things are not so grammatical that you can define, okay, this is a participle, this is a this, in great detail, right? So even like noun says, I think plural and singular are not distinguished in their case, which in standard English people do distinguish. Yes?
What was that? Like the obozo, so what?
This is a named entity. Proper noun.
Proper.
So named entities.
And the contracted,
This one?
Sentence first word. Last
Oh,
sentence.
this is I think this is not a U, this is a O. It's like cropped, I cropped it, thank you God. So this O would mean pronoun, I think. O here also. What else is O?
That's like the
Contracted form of U, but they don't, no. So this just got cropped here. The image, it's a full O.
Okay.
Sorry, it's just the image got cropped there. Dollar is number, I think, and yeah. So this is an exclamation, Elmau. So it's an exclamation. But what they say is this, right? So they give some interesting statistics of how many hashtags and all these things they observe in the data. But one thing they struggle with is this. So often apostrophes are often omitted. So you don't. So you just put a S or Z with the word instead of putting an explicit apostrophe when you were to say, let's say, some things. So and then they have things like IMA for I am going to. So just IMA means I am going to. How many of you knew that? Yeah. So you just write IMA short of I am going to. Now what tag do you give this? Because this is a challenging thing. You have a verb here, you have a noun here, a pronoun here. So what tag you give? So they came up with a new category, actually 4 new categories. So when there is a noun or nominal means both noun and pronoun, or a proper noun, and then on the other side if there is a verb or a possessive. So possessive is those apostrophe s kind of thing. So then they have 4 different tags. So if a nominal and verb comes together, like I'm gonna, so this gives you 1 tag. If it was a nominal and a possessive, it would give another tag. If it's a proper noun and a possessive, it is another tag, and a proper noun and a verb together. I don't know, can you think of an example of proper? Maybe S or Z sometime as he is, right? So instead of saying he is something, you say he's, H-E-Z something. So those kind of things, you will use nominal and verb. But if you did it with a name, then you would use proper noun and possessive. So these were the 4 more tags that they had to come up with to explain this. The other option, of course, would be you split them up. So you say IMA is not a single token, I is a token, M is a token, A is a token. And I stands for pronoun, M for auxiliary verb, and A for verb maybe. But that would be very, very weird and hard. Things will get confounded. So this is what they did. Now what kind of features they use? So usually for pause tagging, you use things like what is the previous word, what is the next word, what is the previous tag. So these are standard features. Then you look at whether the word is capitalized or not, what is the last 3 characters of the word, first 3 characters of the word. So these are the common, and what the word itself is. So these are common tag features that you use. On top of it, they use some new features. So one is they call Twitter orthography. So Twitter orthography features are they had a set of regular expressions which try to map, which try to signal something about the thing. So does it start with a hash? Could be one Twitter orthography feature. Does it start with an at? Is another feature. So similarly, is it all caps? Could be one feature. Then they had another feature called names, which are frequently capitalized tokens. Now named entity recognition, and we have been struggling with it for a very long time, it's one of the hardest problems to tackle in Twitter, because it's not only names of celebrities and places and organizations, but also names of any, Jack, John, anybody there, right? Every name comes up in tweets, and you have to keep identifying them. People do not capitalize properly. So how do you do it? So one way to do it, what they suggested is you look at the entire corpus and see which tokens are very commonly capitalized and get a score of that and use it somewhere. Of course, they had a traditional tagging dictionary. Then this is another thing that they did, which was, today we would do it differently. So what they did was they took a large corpus and tried to get context vectors for all words and clustered words and use those cluster. So this is called the distributional similarity clusters, and use the cluster ID as one of the features. But today probably people would do what? Word2vec. So people would use instead word2vec because they work better than traditional distributional similarity. And then they used also some phonetic normalizations using metaphones. So metaphone encoding is one way of phonetic normalization. You actually replace the given string with another string, and that particular string was also used as a feature in the thing. So they did some Twitter specific things. So here are the results that they show. So yeah, I said 95, I was wrong actually. Inter-annotator agreement is 92. So human annotators do not agree more than 92% of the time. and their best system probably was doing 89, which is pretty not that bad actually. It's a 3% kind of difference, and these are, you know, when you do not use something. So they get this when, let's say, they do not use the names feature, but everything else is used. And Stanford is working 85%, I just showed you. Okay, so we will move on to just a few examples now. I mean, there are many such cases where people have built things from scratch for Twitter. I'm just showing this one example because this was one of the first, and I think they very nicely, you know, do all the steps. Now, once people now are working on post tagging, so a lot of work after that also have happened on post tagging, but now they can take their post tag set, they can take their data and work. But they were the first, so they had to do all the things, starting from defining a tag set. So any questions up to here? Yes.
So when you mentioned about I am gonna and I am you, and so how is it handled in the case of normalization? Like when this was a great AI is becoming this was fine, but what about I am?
Yeah, so this is a very interesting question, right? So ideally, if you are normalizing it to I mean, very standard English, which any standard English processor can process, then you should do I am going to.
Yeah.
Yes, so that's what is expected.
Could also be I am or something.
So that's context dependent. That is okay. That the language model will try to resolve, right? So the channel model will tell you IMA could be I am AMA and A, or I am going to. And the language model will substitute each of them and score and tell you what makes sense here. So if I am, after IMA it's a verb, then it's most probably I am going to do something. And after IMA, if it's a noun.
Like both of them need to be handled in the same way, like the techniques work.
So the technique, yeah, so theoretically the techniques should work. But the problem is there are lots of problems. So this is one example where it's still monotonic in the sense that you just expand it. Now, the first technique won't work. The first technique where you look at phonetic similarity and all won't work for IMA, right? So for abbreviations, what we used was a dictionary. So we had a dictionary like ELMA, what does that expand to? Or ROTFL, what does that expand to? TB. So that we used a dictionary, and I will show you. I mean, I was going to tell this. So fortunately, there are lots of such dictionaries. You can just, you know, go search and download. So you can use those. Some of them are better than others, and maybe you have to add a few things based on your data set after observing your data set. But so the phonetic part won't work, but the language model part would still work. If there is ambiguity, you could probably disambiguate. There are bigger problems actually in normalization. Sometimes it's not monotonic also. So and you might, there are ellipses. You might drop entire things which you should have said in normal text. So you might drop pronouns. Pronoun dropping is very common. So you may not say I am going to do this. You could just say going to do this kind of thing, right? And that's meant. So there are also other kinds of problems. Okay, so here I'm just going to tell you some of the opportunities, like funny things people have done with, not funny, I mean they're profound also, but interesting things that people have done with NLP for social media. So I already mentioned about language dynamics, right? Language changes very fast and on social media, and people have used this feature to study several different effects of several different causes and as well as effects of language change. So the first work, it tries to find out what is called diffusion of lexical variation. So what happens is somebody innovates, right? Invents a new word and starts using it, or a small group of people start using it, and then it spreads over the network. And when a large population starts using the word, then it becomes part of the lexicon. So this is how words would typically, new words would come to be used. So they studied the mechanism how that words diffuse over this social media. And especially they are talking of lexical variation, which is like the same word spelt in different ways, how they kind of get conventionalized. The second one, so this is also very interesting. So this looks at a phenomenon called compounding. Often a lot of English words or words in any language are formed by joining words, multiple words, right? So this is called compounding. Laptop, lap plus top. Now, if you look at the etymology of the word, you know that laptop, or think about it, you know that it comes from lap plus top. But if you just, when you are using the word in general or don't think about it, many of you probably would not never realize that it comes from laptop, because the meaning is actually, I mean, if you think of it well, it makes sense, but the meaning has come far from, just lap and top. So sometimes these departures are even more radical. Now, somebody would have started using the word compound at some time, right? So for instance, when email came out, the first people used electronic mail. Then people used e-mail, and then email, even dropped the hyphen. So it became a word. So how that process happens over time. So they studied it with hashtags. So apparently people combine hashtags. So you had a hashtag Bieber and a hashtag Blast, and then people had used those two hashtags separately, and then suddenly somebody started using Bieber Blast, and then everybody now uses only Bieber Blast apparently. So they studied the dynamics of such processes here, and they tried to predict actually, okay, this particular word, compound word or compound hashtag is going to be popular over time. Here are two examples on sociolinguistics and pragmatics. I already talked about, actually I talked about both of them, so I'm not getting into the details of this. The first one is this work on accommodation. They looked at the social media data on and studied linguistic accommodation. The second one is the other work that I talked about, where they looked at the, how one person interacts with a community or a group, and how, so they had like how the vocabulary of the old member, meaning people who do not update their vocabulary, would eventually leave the community, and they can predict who is going to leave the community by looking at how is your vocabulary changing over time. Are you really picking up new stuff? This is another set of very interesting work, which people have done a lot of studies for health and mostly mental health, but some also physical health related issues from Twitter. So the first work, actually it became very popular. It got, I think, the best paper award that year in ICWSM. And Munmunde Chaudhary, in general, she has been working in this space, how to characterize mental illness by looking and predict mental illness by looking at your social media post. So they use a lot of NLP techniques for doing this, like is it a depressed post, is the sentiment negative, and things like that, and try to predict. So she has done a lot of work on depression, and some of those work are, very interesting, and also, a lot of people after looking at these kind of things are doing a lot of studies on mental health. People can do also this one I was talking to, in fact, Kiran last week or last week. So this got a lot of press. Now when I asked, so this says from I love you babe to leave me alone, how romantic relations break up, and they tried studying those dynamics on Twitter and trying to even predict which relations are going to break up. And so he, when I asked him about this work, he said, oh, this was one of my silliest work, and I don't know why it got so much of press and all. But yeah, it does happen. Then the people have also done not only mental health, like things like what do you call them, like the smoking and alcoholism. So trying to drug addiction and all those kinds of things. That how you can see. So people try to predict who is addicted to what kind of drug. So I saw a paper which tries to look at your text and says, okay, you are under the effect of LSD, or you are under the effect of cocaine, or you are under the effect of, so what drug you are under the effect of when you are writing this. And from that they can do take remedial measures. And of course, the last one, I don't know who if anybody at an industry scale is doing this, but this looks like really doable, which is all of us have a different language model, if you think of it, right? Our language usage is very different. Now, usually it's very difficult to customize it to every individual. That's why speech recognition system in earlier days would work only with your voice, and you had to train it with your own data. And that was a painful process. I remember it would give me lots of text and I had to read it out, and after that it would start working. So same for even otherwise language, right? The way we write language is very different. This work, what it tries to do is, it builds a generic language model based on everybody's data, but then kind of make it more specific to your language use. Okay, so we are kind of done. Briefly, we talked about that NLP for social media has several applications. It's a big data kind of, it's a big data in the sense there is a lot of volume variety. There's a departure from standard language. It's in between speech and text. And there are also lots of opportunities for NLP researchers here because you can do lots of socially grounded studies. So Seiza will talk about it a lot more in her computational sociolinguistics lecture. And we have seen that the standard tools do not work well, and you have to do either normalization or build systems from scratch. So I think that's the most important takeaway. Now, there are other things which we did not talk about. I don't know if anybody is going to cover. So one is, how do you collect social media data? This is a very practical thing. I mean, of course, Twitter gives you an API, but not everybody gives you an API. And when you have an API, still the data collection is non-trivial, because what kind of data you want to collect, and those kind of things are important. Are you going to cover some of them? Yeah. Then data annotation, of course, it's a field in its own, and we won't have time to cover how to do all these things. I did not talk about pre-processing. So normalization is an end-to-end system. I presented it almost like an end-to-end system, but actually you can break it up. So even like when you don't normalize, still you need to do some pre-processing because the data might be very noisy. The data, the way it comes up. So very simple things like, regular expressions for detecting URLs and all. Fortunately, a lot of these are available and you can just rely on available stuff. Handling multilingual data, Kalika is probably going to talk about it a little bit in her talk. And we did not talk about domain adaptation and style adaptation. So people have shown what works for Twitter may not work for Facebook, and what works on Facebook may not work for Reddit. So each of them are very different from each other. So how do you build systems which you can easily adapt to these different domains? Some tools and resources that you could use. So as I said, dictionary of slangs and abbreviations are very easy. So ask any of us, we have been using, so we can tell you where to get those. Regular expressions for URLs, mentions, tags, etc. are also not hard to find online. And if you need anything to do with like language identification at word level and stuff like that, again, ask us. We have the tools so we can help you. Then the post tagging work actually comes from this CMU group. It's called you go to this website or search for just tweet NLP and you have lots of things, post taggers, tokenizer. They start everything with a TW for tweet. So tokenizer, Twibo parser, there's a parser, and they have all kinds of data. There is also sentiment analysis tools which are available, but almost all these things are available for English. So if you want to do anything for Indian languages, you have to write to specific people. So I think, for instance, IIT Kharagpur has a sentiment analyzer for Hindi tweets. IIIT Hyderabad might have a few things. Maybe you guys have a few more things for. Do you have anything for Indian languages?
So sentiment analysis too, and
Post tag. So most of these probably you can't just go somewhere and get. You have to write to people. Yep, that's it. Questions?
Virality prediction or popularity prediction. So this is also something that comes up in computer vision, predicting memes or images that get a lot of attention. A lot of the memes are also not just visual or not just text, they're both. A word like this very recently came up for and it's associated with drums. So is there any work that looks at both images or visual?
Yeah. So there are work which looks at both images. I have seen work which looks at both images and text. Now, whether they are for virality prediction or not, I'm not too sure, but I think there are work. So Dhruv Batra from Georgia Tech and Devi Parekh. So they are working on some of these, how you take image features and text features and combine and predict things. So they're doing some very cool stuff also where you are given a set of images and you have to reorder them in a way so that there is a story and then you write that story. Yeah. I'm trying to think if there is any other. Virality?
There's a workshop this year.
Yeah, on virality?
Yeah, using vision and language.
Vision and language together.
One question. So you have been studying social media text for the last several years. So I understand some transient things like two hashtags getting combined, or definitely vocabulary changes every day. But apart from that, do you observe any systemic changes in styles or like things you said, like which would take 300 years on offline world can take 3 years on, or even 3 months on. Have you observed anything?
So when we talk of language change, right? So some of the things we talk about are these words, word pronunciations getting changed and stuff like that. So there are two kinds. So one is one lexical entry entering, which we just talked about, and that is probably not that long term. Even in real language, that may not be that long term. For legitimizing that change, it might take a long time. But the entry, of course, happens at one point and suddenly gets popular. But things like, let's say, the great vowel shift. So how the pronunciation of all the vowels in, let's say, the Germanic languages changed. That took a long time, and that actually completely changed the way English looks today from, let's say, German looks today, and so on, right? So these kind of changes also happen. Like, for instance, dropping of vowels, I can compare to that, right? So dropping of vowel is one very common thing, but it started with CMC in general. So even with texting language, you had dropping of vowels, and even now with this, so probably you are talking of that kind of change, right? So I'm trying to think what are other that kind of things that suddenly would, have started happening or something. I'll have to think. Something which is very generic and happens everywhere.
So since people are using a lot of Facebook media nowadays and use a different type of language models, website, is there any evidence that it's changing, that writing this is changing the way you write formal?
Yeah. So see the second one. Has social media changed the way we speak and write English? Yeah. So there has been apparently. Some years ago, these days it's kind of standard, but some years ago, there was an article where one kid, apparently, maybe 10-year-old kid, wrote an essay, and it had all this kind of social media language. And the teacher, of course, didn't like it. And the question was, I think this is what this article is about. And the question was whether this is appropriate or not. Is it acceptable or not? And of course, there are both the sides and they debate. But it does influence. At least I observe in my own writing, it does influence, right? So things like you for YOU or BTW for by the way, I use in even very formal emails.
Is acceptable telling images
Yeah. Nothing is worrisome. I would say even if the entire language changes, it's okay. But I don't know. I mean, things might change very fast. In the sense, in a couple of generations, it might be very different. Yeah, so one example of structural change is this, and this just happened a few 2 days ago. So somebody posted some photographs about an MIT IIT robotics workshop, and wrote in that some name, let's say Ram. So ooh la la la, Ram be like the darn thing doing blah 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 something. So some professor commented on it that ooh la la la, he quoted ooh la la la, Ram be like this, what does this mean? You know, so I actually it's interesting. So Steven Pinker wrote an article about how the use of like has changed over time. And if you see, like we use for almost everything now. So like he said X, we would say he was like X. So this is very common. So this is a structural, I mean, not structural in the sense of syntactic change in the language, but at least the lexical item assumes a new syntactic role. Yeah. One way I go first.
Are any of these computation studies informing theoretical thinking? Like for example, you mentioned this trend of dropping pronouns in meta text. So, and we have in languages class of languages, program language. So factors like ease of articulation, which is very well evident in platforms like Twitter.
Right.
Like, are these supporting any theoretical claims?
So lot of these studies actually are validating. So I don't know of any study which comes up with a whole new linguistic insight just by looking at social media. So most of these have been like validating what is already known. So for instance, even our study on language use in multilingual society is validating some hypotheses which linguists have already said.
You get the purpose.
Okay, one last question.
So all the corpus that we're connecting for mode fixing, maybe it's like a Facebook post from OTTV or from Twitter. All these are domain dependent, right? So we're connecting for the synchronization.
Okay, topic dependent.
Like, do you have any strategies for creating a corpus that's not a domain dependent? Because we sometimes after
No, so this is true even for regular corpus, right? So when you collect a corpus, if you had collected all news or all science news or all sports news, it will be domain dependent. The way you handle this is you basically make sure that it is balanced. So you take, let's say, broadly what people talk over Twitter: personal stuff, politics, sports, entertainment. So let's say you divide and you make sure that you have 20% from each of these categories, and then you might further subdivide, and so it's like that.